Hey, welcome back. Today we are going to continue to work with the power rule. And just as a reminder, basically what the power rule says is if you're trying to differentiate a term that has x and some exponent, then to differentiate that without having to go through the limit definition of the derivative is to just bring down that exponent down to be a coefficient and reduce the power by 1. We also talked about how if there's a coefficient on x initially that you would multiply that n by that coefficient. But you got a little bit of practice in, and I think we all kind of agree that it's going to be a lot easier to handle derivatives using the power rule versus the limit definition. So yeah, let's just get a little bit more practice in. Really want to make sure that we have this skill down. We're going to introduce just a couple of little things, but for the most part today, we are just going to be practicing what we've already learned. So 1a here gives us a function that's in factored form, and we're asked to find dy dx, which, as we know, is just the derivative. Okay, this is the same thing as saying y prime, or just saying like the slope function, or the function that describes the slope of y. So what we need to do is actually just multiply this out. Okay, we've got x squared times x is x cubed, x squared times negative 5 is minus 5x squared, 3 times x is going to be plus 3x, and 3 times negative 5 is going to be negative 15. Now we can apply the power rule to each of these terms individually. So y prime, which is just another way of writing dy dx, just a notational difference, is going to be 3x squared. Right, I brought the exponent down and reduced it by 1, minus, this one's got a coefficient, so I've got to make sure to multiply. 2 times 5 is going to be 10, x to the first power, but I'm not going to write the 1, plus 3. The slope of any linear term is just going to be that coefficient, and then the slope of any constant term is just 0. We're not going to write plus 0, just like we're not going to write x to the 0th or the 1 and x to the first power. So that's it. There's our derivative. Letter B. Okay, so this looks a little bit different. This doesn't look like the kinds of equations we worked with last time because this looks more like a rational expression. But this is a specific type of rational expression that we can use the power rule for, and it's one where the denominator is just a monomial. Now, when the denominator is not a monomial, we've got to find some different techniques to handle those. But when it is just a monomial, meaning when this denominator is just a single term, we can actually just divide each term by of the numerator by that denominator and rewrite this so it's more in that polynomial form that we like with the power rule. So dividing each term here, we've got 3x to the 5th divided by x squared is going to be 3x cubed. We're just reducing the exponents, or finding the difference between the exponents, plus 6x squared divided by x squared. Okay, we can use our exponent properties here and just subtract, and we get x equals, we get x to the 0th power, which is just 1, so this is going to be plus 6. And then finally plus, and then here I've got 2 over x squared. And just as a little reminder here, when we've got a exponent in the denominator, we can rewrite that using a negative exponent. And so now we're ready to go ahead and differentiate. So dy dx, which is the same thing as just saying y prime, is 3 times 3 is 9, x squared. The slope of a constant function is just 0. And then with this other term over here, we've got negative 2 times 2 is negative 4x, and then 1 less than negative 2 is negative 3. So a little bit different. We had to work a little bit to get our equations into that polynomial-ish form that we like to use with the power rule. We don't want to just go ahead and use the power rule if we've got two binomials being multiplied like an A. Also with B, we've got something that we need to do to sort of set up the equation to get it into that form to where we can just directly use the power rule. So you want to be on the lookout for equations like this that might look like the differentiation is a little bit harder than it is. Number 2 says determine the equation of the normal line to the graph. Okay, so this is our f of x. All right, this is f of x right here, and I think it might be wise to just go ahead and write this since we're probably going to be talking about derivatives. I haven't even discussed what a normal line is, but let's get this into standard form here. And to do that, I'm going to multiply the 4x squared to both of these terms. So 8x to the third power minus 20x squared is going to be my f of x, and so that's the graph of that. What it's asking for is the equation of the normal line. So we need to know what normal line means. So the tangent line at x equals 1. Okay, let's talk about tangent. We know what a tangent means. So here's x equals 1. The tangent line, I'm just going to try to sketch this, so it's going to be not perfect, but just kind of freehanding what that looks like. Looks kind of like that, right? This is the line tangent to f of x at x equals 1. So the normal line is going to be the line that is perpendicular to the tangent line at that point. Okay, what I mean by that is that the normal line is going to look something like this. Maybe I'll use a different color because our curve is red here. So I'm gonna use green, and I'm just estimating here. This is just a sketch. It's not going to be perfectly perpendicular, but that's what we're going for. So this is what we mean by the normal line. It's the line that's perpendicular to the tangent line. And specifically, where are they intersecting is the point at which, we're interested in. So if we want the normal line at x equals 1, that's going to be perpendicular and intersecting the line that's tangent at x equals 1. Now, this question doesn't actually ask for this, but I think this would be a good opportunity to just take a little detour here and find the equation of the line that's tangent to f of x. So the equation of the line that's tangent to f of x is going to be in the form y minus y1 equals m times x minus x1. All right, we've already written several lines like this. This is going to keep coming up, and we're going to continue to write them in point-slope form. The coordinate that I'm going to plug in for my x1, y1 comes from the x value that I'm interested in the first place, and the y coordinate of that point of intersection. So to find that y coordinate, I'm just going to substitute in 1 into my function. So I'm going to need this as for my y1. So f of 1 is equal to 4 times 1 squared times 2 times 1 minus 5. So that's going to be 4 times 2 minus 5 is negative 3. So it's going to be negative 12. So that's going to be my y1. That's going to be right here is at negative 12. So I've got my y1 is negative 12. My x1 is at 1. So we got y minus 12. Oh, that should be plus 12. Equals a slope, which I don't know yet, and then x minus 1. So now I need to figure out what that slope is. That's where the derivative comes in. Remember that the derivative is just the slope. So I'm actually going to clean this up a little bit here. Give myself a little bit more space because I want to write the derivative of f here as well. I don't really need too much room to do that. Now that we have the power rule, we can just get it in one step. So 3 times 8 is going to be 24. X squared minus 40x. So that's the derivative. That's the slope. And so since I want to know what the slope is when x is 1, I can substitute in 1 into this slope formula. All right, so the slope here is going to be, well, let's find out. If I plug in 1 here, so what I want here is the value of the slope when x is 1. It's going to be 24 times 1 squared minus 40 times 1. So that's just 24 minus 40, which is going to be negative 16. All right, so the slope, just to be clear, we're not actually answering the question they asked here. This is just the tangent line. Okay, so this is, well, it's this blue line that we drew earlier. If we want the line that's normal to that, it's still going to intersect at that same point. So my x1 and y1 are going to be the same. But what's going to be different is the slope. And this is just something that you got to remember from Algebra 1 and Algebra 2, is that perpendicular lines have slopes that are opposite, meaning one's positive and one's negative, reciprocals. Okay, opposite reciprocals. So we're going to have the exact same equation as we had for the tangent line. So it's going to be y plus 12 equals some slope times x minus 1, same points, right? But the slope is going to be the opposite reciprocal of the tangent line. So since the slope of the tangent line at this point is negative 16, the opposite reciprocal of that would be 1 over 16. So this right here is the normal line. Now, I've got a lot written down on this on this particular problem. If you just follow the steps, you don't have to necessarily find the tangent line. You really just need the slope of it. So you don't have to go through that. I just thought it would be a good opportunity for us to write another equation here, since this is going to be a common question throughout the course. All right, number 3, determine the instantaneous rate of change of this function. Now, let me just take a moment here and talk about instantaneous rate of change, because I think something that I haven't really done a good job differentiating here with, sorry for using that word again, but is the difference between instantaneous rate of change and average rate of change. Okay, so let's just take a little breather here and kind of go back and make sure we understand the difference. Okay, so when we talk about average rate of change, that is going to be the slope or the rate of change that we find between 2 points on our function. So let's say we have, a graph that does something like this, and we want to find the average rate of change between 2 known values on the function. So to find that average rate of change, we just calculate the slope, right? Like these are 2 separate points, and so finding the slope of the line that goes through there, this is a secant line, is going to give us that average rate of change. So the average rate of change equals the slope of a secant line. Whereas instantaneous rate of change, this one is actually more of an accurate representation of the slope at any point. The average rate of change just kind of gives us an idea of what to expect the slope to be at any given point, but the instantaneous rate of change tells us exactly what the slope is at a particular point. So instead of finding the slope at a secant line, we're finding the slope of a tangent line. So I just want to make sure we understand the difference here moving forward. I don't think I did a really good job earlier explaining the difference between these two. So when it says determine the instantaneous rate of change at a point, you're just going to find the slope or the derivative of this function and then substitute in 9. If it's asking for an average rate of change, a lot of times you'll see this on like those tabular problems that you've had on a couple homeworks, where you're given a table and it's asked you to estimate the average rate of change or find the average rate of change between 2 x values. That's average rate of change, but instantaneous rate of change happens at just one specific point. So let's go ahead and find the instantaneous rate of change, or the slope at x equals 9. So if y is 2 times the square root of x, which I'll rewrite as 2 times x to the 1/2, times x plus 3. I want to first distribute this coefficient to both x and a 3. That's going to give me 2 times, and then if you're a little confused about how these exponents get combined, just remember that whenever you multiply two powers that have the same base, you're going to add the powers. So if you don't see a power there, it's just 1. So this would be x to the 1 plus 1/2, which would be 3/2. And then plus 6 times x to the power of 1/2. All right, so now I can find the derivative by using the power rule. 3/2 times 2 is just going to be 3. So if I subtract 1 here, 3/2 minus 1 is going to be 1/2. And then 6 times 1/2, half of 6 is 3. And then subtract 1 from the exponent, it's going to be negative 1/2. Okay, and that's pretty much my answer. Now, well, not my answer, but this is the derivative. This is going to describe the slope or the instantaneous rate of change at any x value. So if I want this evaluated at 9, so if I want to find the value of the slope when x is 9, I'm going to have to substitute in 9 to this. Now, if I don't have a calculator, sometimes it can be harder to recognize what this should actually equal without, with dealing with these rational exponents. So it might actually be a little easier, I think, if we go back and rewrite this using the square roots. So recall that raising something to the 1/2 power is the same thing as root 9. So you have 3 times square root 9 plus 3 times 1 over the square root of 9. And now it's just a little bit, I think the mental math is a little bit easier when you write the square roots just because you're more used to them. Algebraically, obviously, writing square roots as rational exponents makes sense. But I think when you're trying to evaluate it on the back end, sometimes it's advisable to go back and rewrite a square root, and then you can just kind of come up with the answer a little bit easier. So yeah, so the slope when x is 9 is going to be equal to 3 times 3, which is 9, plus 3 times a third is just 1. So 9 plus 1 is 10. So the instantaneous rate of change when x is 9 is 10. In other words, the slope of the line, the tangent to the curve, is 10. All right, we got one last problem for you. Like I said, not a whole lot of problems here. It's just really making sure we got that power rule down and seeing how we can apply it, especially to functions that look a little different, that don't look immediately like that we can write them in that polynomial form. But we can. Now, this number 4 looks a lot harder than it really is. This is the kind of question that you're going to be given on the AP test, almost guaranteed at some point, where they're trying to determine whether or not you understand the limit definition of the derivative. Now, because we're going to learn all these tricks on how to find derivatives, there's probably not going to be a question where it's like, hey, find the limit of this, or find the derivative of this function. You have to use the limit definition of the derivative. There's probably not going to be a question like that. But what there will be is a question like this where you're expected to recognize the limit definition when you see it. So in other words, like if I try to evaluate this kind of like, try to approach it like I would in the first unit where, try to multiply out the h plus 6 and distribute the 3 and all of that, that's going to be a huge pain, right? You don't want to multiply all this to the power 6. And quite frankly, I don't want you to do that either. What I want you to do is recognize that this kind of looks like that limit definition derivative, right? Which is this, f of x plus h minus f of c all over h as h goes to 0. And you can kind of look at both of these and hopefully you can kind of see that, yeah, that does kind of look like that. And so what you're trying to do is you're trying to figure out, okay, well, if I recognize that that's a limit definition, what function am I actually trying to differentiate here? And so Oh, f of c. Nope, that should be f of x. I don't know if I just didn't get that in there or what. But so f of x here is going to be right here. Okay, so if f of x is 3x to the 6th plus 5x to the 4th, hopefully you can see how then f of x plus h would be 3 times x plus h to the 6th plus 5 times x plus h to the 4th, which is what we see right here. So once you recognize that this is actually just the limit definition of the derivative, then what this whole expression actually is just going to equal is just f prime x. Yeah, we already know what f of x is. So this is equal to the derivative of f of x, which in this case f of x is 3x to the 6th plus 5x to the 4th. So using our power rule, we can find this derivative without too much trouble. 3 times 6 is 18 times x to the 5th plus 20 times x cubed. And we did not have to multiply all that out and find the h to cancel out or anything like that. All right, that's the end of today's notes. Thanks for watching, and I'll see you next time.